So I got to the section 3.3.2 towards the bottom of page 63, which is entitled Mean and Variance for GLM Distributions. So just to remind you a little bit about a GLM, we've got this diagram which I've drawn a few times now. So we have a linear predictor, which is essentially the same idea as for the standard linear model. So this is xi transpose times beta for a particular observation. So eta I is the linear predictor for observation I. Okay, so that is related to the mean of the observation via the link function. So this is represented by this side of the diagram. So eta I is g of mu I, and if h is the inverse function of g, the inverse link, then mu I is h of eta I. So that those two functions, g and h, relate the linear predictor and the mean of the observed value. Okay, and then we also have this connection on the right to the canonical parameter of the distribution theta I, and right at the end of last lecture we showed that this could be represented by saying that mu I was b prime of theta I, and b here is the function which appears in the form of the likelihood for a generalized linear model distribution. So this is a particular function which we know from the formula for the generalized linear model density. And b prime, of course, just means it's its derivative. Okay. So we have these facts where we're applying these results about the score statistic. So the score statistic is defined as the derivative of the log likelihood at our true values, theta and phi, given an observation y from our distribution. Okay, so there's a theorem, which was theorem 2, which says that the score statistic, which is a random variable because it depends on y, which itself is random, it has mean 0, and it has variance given by the minus the expectation of the second derivative of the log likelihood. So we're now going to apply these results to a GLM distribution. In a GLM distribution, the log likelihood has the form at the top of this slide, and that's what happens if you differentiate it twice. Okay, so in the last lecture we worked out the consequences of differentiating it once, so the middle equation on this slide, and that actually told us that b prime was the right thing to have in the diagram where we've got it on the left hand board. Okay, so I'm now going to talk about what happens with the second derivative. So if we just do the differentiation, we can see that the second derivative of the log likelihood is w over phi times minus b double prime, the second derivative of b, and that's with respect to theta, as b is written as a function of theta. Okay, so I'm going to now skip over the slide that I did at the end of the lecture where we did the version with the mean, and now move on to the bit where we're talking about the variance. Okay, so this is the sort of second paragraph from the bottom of page 63 in the notes. So that formula that we got for the second derivative didn't actually depend on y. Okay? It's got w over phi times a function of theta, so there's no y in it. So it's not in fact random. So the second derivative, which we know from here, is gives us the expectation would give the variance of the score statistic, but the variance of something which is, so the expectation of something which is constant, it's not random, we just ignore the expectation part, because the expectation of a constant is that constant. So the variance, in fact, variance of the score statistic will be minus that second derivative of the log likelihood. Okay? Now, again, if we go back to the previous slides, we can see an expression for the score statistic in terms of y. So what this argument has told us is that the variance of the score statistic is the second derivative of the log likelihood, so minus the second derivative of the log likelihood, which involved b double prime of theta. Okay. Now the score statistic is a linear function of y. Okay, just remind you again what the score statistic actually was in this case. So the score statistic is the derivative of the log likelihood, so it's w times y minus b prime of theta divided by phi. So the variance of the score statistic is going to be w squared over phi squared times the variance of y. And that's just by the standard properties of the variance when you apply linear transformations to a random variable. Okay, so the variance of the score statistic by this is w squared over phi squared times the variance of y. So that means, because we know what the variance of the score statistic is in terms of b double prime, we should be able to see what the variance of y is. Okay, so if I get back to where we were, so that was here, we can actually see there's a little bit of cancellation involving the phi's and the w's. So we can see that the variance of y itself is phi over w times the second derivative of b double prime of theta. So that is the variance of y. Now, if you remember, we had some assumptions about the distribution for a generalized linear model, and one of those gave us a form for the variance of our observations. Okay, so this is back on page 57, and that variance was going to be phi over wi, where wi is the weight, so it corresponds to the w here, times a function which we called v. Okay, and that v was written as a function of the mean, so we wrote v of mu I. So we can see here that v of mu I should correspond to b double prime of theta I. And so if we look over here, we have our relationship between mu I and theta I. So mu I and theta I depend on each other. So if we can write it as a function of theta I, we can also write it as a function of mu I by looking at the relationship here. So that in fact tells us the relationship between this function b that we've got that appeared in the third assumption that we had for a GLM distribution, and that variance function v. Okay, so that tells us if we rewrite b double prime, which is a function of theta, the canonical parameter, if we rewrite it as a function of mu using the relationship over there, that actually gives us the variance function. So we can see that that second assumption about the variance wasn't really necessary. The third assumption about the form of the distribution is enough, and we can use what we've just shown to deduce what the form of the variance must be. Okay. So, I now want to move on to section 3.3.3. So section 3.3.3 essentially summarises the types of distribution for which generalised linear model approach is appropriate. So, in principle, any family of distributions which satisfies the general form given in that assumption 3g, back in section 3.1, can be used. The most common distributions to which generalised linear model theory is applied are the ones here. So in particular, the Poisson and the binomial, both of which we've discussed a bit. Binomial we've discussed quite a lot, the Poisson a little bit. We can also use the gamma distribution. And in principle, we can use the normal distribution as well. And as I'll say in a minute, essentially the normal distribution for the generalised linear models, if we think about it that way, it's essentially saying that we can put the original normal linear model that we had in the first couple of parts of the course we can write that as a generalized linear model. Okay, now in the notes there's a table, which I haven't reproduced in the slides because you wouldn't be able to read it because it would be too small, which gives the various parameters of the generalized linear model form which apply for each of these distributions. Okay, so it tells you the phi and the w, so the dispersion parameter and the weights, and it gives you the function b, which, as we've seen, actually tells you how the mean relates to the canonical parameter and also the variance. And it also gives you the first and second derivatives of b, and also the function c, which in practice is generally going to be treated as a constant, although it does depend on the dispersion parameter phi, so you have to be a little bit careful. You have to be aware that it's there. Okay, so a little bit more on each of those distributions. So we've already talked quite a lot about the binomial, circumstances where it might apply, and how to fit a binomial generalized linear model in R. Okay, as we've seen, we don't actually take the binomial value itself, the number of successors, S. Instead, we take the proportion of successors, S over N. Okay, so that's what we take as the response variable for a binomial. So a little bit about the other distributions. So if we take the normal distribution and we use the link which is the identity, so in the diagrams over here, these two functions will be the identity, so eta I and mu I will in fact be the same thing, then that actually just recovers the standard linear model. So we can write the standard linear model as a generalized linear model, if we want to, with the identity function as the link function. Okay, now, in practice there isn't a particular reason why you might want to do that, but it does show you that the generalized linear model really is a generalization of the standard linear model. There might be some circumstances where you might want to use a normal model with a different link, and in those settings you would actually be using something which was different from the standard linear model. Okay, Poisson distribution is useful for count data, where you have counts of something, particularly in a situation where it's clear that the binomial distribution doesn't apply. The Poisson distribution is often a first model when you're counting things. That might be counts of accidents, counts of people having some disease, all the things that the Poisson distribution is a standard model for. Finally, back in chapter 2, we talked about transformations of random variables for the standard linear model. And one thing we talked about is a situation where the standard deviation seems to be proportional to the mean. And in that case, we discussed potential transformations of the data which you could use and then apply a standard linear model to the transformed data. Another possibility is to use a generalized linear model. And if you use a generalized linear model, a natural choice, because it satisfies this property, is to use a gamma distribution as the model for as a generalized linear model for the data. So in fact, on one of the exercises, not one of the ones for handing in, I've asked you to compare what happens where we had a data set before that you've used a transformation on, and to use a gamma generalized linear model instead and compare what happens. Okay, task 11 invites you to verify the different values in the table. So that means getting the probability density function for the distribution in question in the generalized linear model form. Once you've done that, that's actually the difficult part. And then you can identify what B is, and then of course you can differentiate B and get hold of the other entries in the table. So we have already done that for the binomial. There was an example further back in the notes where we did that for the binomial. So the task is essentially inviting you to check the binomial calculations and then try the same thing for the other distributions. Okay, I will put solutions to the tasks on mole as well. Okay. A bit further back in the notes, we were talking about how we fit a generalised linear model in R. And we said that R has a default assumption as to what the link function actually is. And R's default assumption is usually that the link function is what is called the canonical link. So in this section, so this is section 3.3.4, I'm going to explain what the canonical link is. Okay, so again at this point it will be useful to bear in mind the diagram over on the left hand board over there, which shows how the mu I, eta I and theta I are related. Okay, so here is the density function again for a generalised linear model. Okay, so it's exponential of y theta I minus b of theta I for this important function b, divided by the ratio of phi and wi. Remember that in many situations phi and wi are known to be, or at least one of them is known to be 1. Particularly in a Poisson, they're both known to be 1. And then we have this extra term c, which is a function of y and phi. Okay, so that's the density function for our generalised linear model distribution. And we know that the mean is the link function, so the inverse link function applied to the linear predictor, which is eta I. Okay. So we've seen some relationships between between the mean and the canonical parameter theta. So that's the other thing in there, the b prime on that diagram on the board over on the left. Okay, so in fact we can say that these two things are both equal to the mean. B prime of theta I and h of the linear predictor, those are the same thing. So they're both the mean. So we can write the linear predictor by composing the function, this function with this function. So eta I is g of mu I, but mu I is b prime of theta I. So the linear predictor is g of b prime of theta I. So here this represents composition of functions rather than multiplication. Okay, so the linear predictor is g of b prime of theta I. Now, we could make a special choice of g, where g is the inverse of b prime, and so this function, this composition, g b prime, is actually equal to the identity. Okay, so if we choose g to be the inverse function of b prime, then the composition g b prime is the identity function, so the canonical parameter theta I and the linear predictor eta I will be the same. Okay, and that choice of g is called the canonical link. So the canonical link is a choice of the link function such that the linear predictor eta I and the canonical parameter theta I are the same. So that's what the canonical link is. Okay. Now, we've already seen in our discussion of the binomial distribution how the canonical parameter relates to the mean for the binomial distribution, and we saw that in that case it's done by the logistic function. Okay, so b prime of theta I, the mean expressed in terms of the canonical parameter, is the logistic thing e to the theta I over 1 plus e to the theta I. Okay, so we've already seen that that's how the mean depends on the canonical parameter there. Now what we're saying is that for the canonical link, the mean is going to depend on the linear predictor in the same way. So you have the same function, b prime here, is also going to be the inverse link function h. And that's one of the examples of links we've discussed. It's the logit link, where the inverse link function is then the logistic function. So the canonical link function for a binomial generalized linear model is the logistic link, or the logit link. Okay, you can do the same calculations, and this again involves getting the distribution into the suitable form for generalized linear model, working out what the function b is, and then you can work out the canonical links for other distributions as well. So for the normal distribution, it won't come as much surprise that the canonical link is the one which actually leaves you with a standard normal linear model, which is the identity link. Okay, so for the normal distribution, the identity link is canonical. For the Poisson, the canonical link is the log. Okay? In both cases, if you use a GLM in R with those families specified, then you will find that the default choice in R is to use these links. The gamma distribution is a little more complicated. If you do the calculations, you'll find that the canonical link for the gamma distribution, as we've defined it, is the negative reciprocal. Okay? So that means that g of mu I would be minus 1 over mu I. Now, that might be regarded as a little bit annoying because it gives negative values of the linear predictor rather than positive values. So it's common to do something which is essentially equivalent and to use the reciprocal, so 1 over mu I instead, rather than include the minus sign, and in fact that is the default in R. So the calculation of the canonical links say you get the negative reciprocal, but in fact the default for the gamma is the positive reciprocal. Just a quick point about that. For a gamma distribution, the canonical parameter is something which takes positive values. You can't have the canonical parameter of the gamma distribution being negative. So that tells us, again by thinking about this diagram, if you have the canonical link, this means this diagram is actually symmetric and theta I and eta I are equal. So if the canonical link only takes positive values, so if the canonical parameter only takes positive values, and you use the canonical link, then the linear predictor can also only take positive values. So this actually gives us a little bit of a problem potentially, because linear predictors can go negative with particular choices of the data and the parameters. So sometimes that'll be fine, because you'll find that if you do the fitting, then none of the fitted values come close to being negative, and so you don't have an issue there. However, it is something to be aware of if you're using a generalized linear model where the potential range of the linear predictor isn't the whole real line. That doesn't apply for the binomial and Poisson cases. Okay, so I'm just going to say something quick about why the canonical link might be thought to be useful. So the point about the canonical link is that, as I say, that diagram over there is symmetric. The theta I and eta I are actually the same thing. Okay, so theta I can be written as the linear predictor, so it can be written in that way. If you have a different link, you won't have some nice convenient expression for the canonical parameters theta I in terms of the parameters. Okay, so here, the real parameters are the betas. Those are the coefficients of the regressor variables. So if you have the canonical link, your canonical parameter theta I is a linear combination of the parameters. But if you have a different link, then that's not the case. If you write the log likelihood down for a generalized linear model, so you can just get this by taking logs of the general form for the probability density function of a linear model, generalized linear model, it looks like this. Now, yi here, i.e. the data, only appears in two places, here and here. Now, let's say that we know phi. So that applies to the binomial and the Poisson models, where we know that phi is 1. So in that case, the log likelihood is really just a function of the theta, because theta is what we're trying to estimate. Theta relates to beta. So phi doesn't relate to the beta. So if phi is known, then really we're just interested in this bit. And so the only bit which has the data in it is now there. So if we know phi, this log likelihood only depends on the data through that term. Now, if theta can be written as a linear combination of the betas, like this, then we can actually rewrite that and say that those terms, the sum over I of these weights wi times the data yi times the canonical parameters theta I, that can be written as this double sum, and we can rewrite that in a linear form involving a matrix, beta transpose times x transpose. X here is the design matrix, as for the standard linear model, times this matrix which I've called n, times the data vector y. So the point is here that this is a linear expression in terms of y. N here is simply a matrix which tells us the weights, the wi, and it's a diagonal matrix, and the weights are the diagonal entries. You might wonder why I've called it n rather than w. That's because in a minute there's going to be another matrix called w. And referring it to n reminds you that the case where these w's most often appear is in the binomial distribution, where they're the numbers of trials. Okay, so if we know phi, the log likelihood actually only depends on the data through these, and these are linear, so we can write them in that relatively simple way. Okay, so that shows you that the canonical link has some properties which mean that the calculations for estimating parameters simplify a bit when you're using it. Now, you don't have to use the canonical link. As we've seen, for the binomial, for example, you can use the logistic link, which is the canonical link, but you can also use the probit link or the clog-log link or the Cauchy link, depending on your analysis. So the canonical link is generally the default link, except for that point that for the gamma you might remove the minus sign, which doesn't really make any difference. However, you should be a little bit careful, because the canonical link isn't necessarily the best choice for a particular data set, and really you should make your choice of link function on the grounds of model fit. So for particularly for the binomial link, where the binomial family, where there are several links available, logit, probit, clog-log, Cauchy, and so on, it's a good idea to actually try and fit the model with all of those links, and if you do that, you can then get a feeling for which link fits the data best. Okay, so that's finished section 3.3. So I'm now going to talk about section 3.4, which is about how we actually estimate the parameters in a generalized linear model. Now, in practice, the answer is that you use a computer. Okay, so if you have a generalized linear model and you want to estimate the parameters, you use R or another software package, and that will fit the model for you. So what's in section 3.4 is essentially a bit of information about what is going on when a computer fits a generalized linear model. So There are some things that are useful to know about in the fitting. So one thing is the covariance matrix for maximum likelihood estimates. So we want the covariance matrix, so the matrix which has the variances of the estimates on the diagonal and their covariances off the diagonal. Now, generally, of course, this is something that we have to estimate. And using a bit of general likelihood theory, it can be found as the inverse of what's called the information matrix for the parameters. So at the moment we'll assume that phi is known, so the dispersion parameter phi is known, so the only things we're really trying to estimate are the betas, the coefficients which appear in the linear predictor. Okay, so in that case the information matrix is a matrix which has, whose entries are minus the various second partial derivatives of the log likelihood. Okay, so you can calculate a second partial derivative with respect to beta j and then with respect to beta k, so you can do it with two different variables, so you get a matrix of second partial derivatives. Okay, and this is called the information matrix. You need a minus sign for on the partial derivatives to get the information matrix. If phi is known, then the phi which appears in here can be taken out as a constant. So you get minus 1 over phi times this second derivative, and now the phi has disappeared from this part. Okay, that's how the information matrix can be calculated, and from there we can get, so this gives us the variance and the covariances of the maximum likelihood estimators for the betas. If phi is unknown, then the usual practice is not to also think of phi as an extra parameter to include in this matrix, but to use the same formulae and replace the phi with its estimator. That may seem a not particularly sound thing to do, but it's a relatively straightforward thing to do. Okay. So one thing that you can do if you have estimates of your parameters and you have you also have an estimated standard error, which you can get from the variance covariance matrix, is you can do tests. You can standardize your value of your estimated parameter by dividing by the estimated standard error. Okay, so that gives us ways we can do hypothesis tests. So we can do a hypothesis test on a particular parameter. Say we might ask, is the parameter of a certain variable, the coefficient of a certain variable, is that 0? We can also do some more complicated tests, as we did in section 1, where we defined hypothesis tests where we had some linear combinations of the parameters. So we can do that as well. Okay, so if we want in particular to test that beta j equals 0, then we can use the estimate of beta j divided by its estimated standard error. Now, you need to be a bit careful with this. As we've said, a lot of what's going on in generalized linear models uses asymptotic theory. And in some cases, and this particularly applies for the binomial or the Poisson, where the means are small. Okay, so in particular, a binomial with a small number of trials, or a Poisson with a small mean parameter, then the asymptotic theory is often not particularly accurate. So although the asymptotic theory gives a normal distribution for the test statistic, it can be better to be a bit more careful, a bit more conservative in your test and use a t-distribution instead. And the usual number of degrees of freedom, n the number of data points, minus p the number of parameters that are being estimated. Okay, so there's a warning here. This test can often not be particularly good, particularly with small data sets. Okay, so after those two sections, I'm going to talk now a little bit about what R actually does to estimate the parameters of a generalized linear model. So what R does is something called, well, certainly one numerical method is that you can use something called iteratively reweighted least squares. So I will just quickly explain what this means, what this title means. So remember that in your standard linear model, you have something like this. So you have some data points, and you're trying to fit a line through them, and it looks something like that. So it's meant to be a straight line. It wasn't a very good straight line. That's a bit better. And we fit this by looking at the distances of the actual observed data points to the line. So these are the residuals. And we try and minimize the sums of squares. Okay, so let's do that for the whole picture. Okay, so we try and minimize the sums of squares. So, in a generalized linear model, the variance depends on the mean. In a way which we know, if we know the mean, we know that the variance depends on the mean. But if the variance depends on the mean, it probably doesn't make sense to weight these two residuals as equally bad. So in this picture, that residual over here is about the same as this residual over here. And in the ordinary least squares estimation, these two would be regarded as equally bad for the line that I've drawn. However, if the variance is larger for mean values like this than it is for mean values like this, then in fact this residual is not as bad as this one. Because the variance is larger here, so this sort of distance away from the mean should be less surprising than it is over here. So if the variance is larger, a deviation of a particular amount, a particular size residual, is not as bad as it would be if the variance was smaller. So that suggests that when we do our least squares algorithm, we want to weight our sums of squares. So we want to have a larger weight for places where there's a small variance, where a big deviation is bad, and a smaller weight for places where there's a large variance, so that a particular deviation is not so bad. So in my example picture, we'd have a smaller weight here, where I'm assuming the variance is larger, than we would here, where I'm assuming the variance is smaller, even though the residuals look like they're about the same. So that suggests that we want to try and weight by something like 1 over the variance. Now, there's a problem in that we don't actually know the mean. Okay? To know the mean, we would have had to have fitted the model. And of course, we haven't fitted the model. That's what we're trying to do. Okay? So, to know what the weight should be, according to what I've just described, we need to have fitted the model. But the weights were something we were going to use when fitting the model. So what we use is an iterative procedure. We start off with a guess of our parameters. We then work out what the mean should be under that guess and use that to do the weighting using the variances. That then allows us to fit a new guess, which hopefully is a better guess than our previous guess. And then we repeat. So we start with a guess. We use that guess to work out what our weight should be. Given those weights, we then fit the model, getting a new guess. then we get some new weights, then we fit the model again, and so on. So each time we fit the model, we re-weight, and we're doing this iteratively. Hence, iteratively reweighted least squares. That's why this process is called that, and that is an informal description of what it actually does. Okay, so we start with an initial guess, which we're going to call B1. Okay, so the B here refers to it connects to betas rather than to the function B that we've talked about over there. So this is just an initial guess of the vector of parameters. Okay, given that, we now estimate some weights for the least squares. Now they're not quite as simple as I described them. I perhaps suggested that they were, I said something like 1 over the variance. Now in fact we don't use 1 over the variance itself, but we need an extra weighting factor which is related to the link function. So we have the square of the derivative of the inverse link function evaluated at eta I. Okay, so as I say, we don't know what these actually are. We have to estimate them using our initial guess. Okay, so those are our weights. And now we'll calculate a vector which we're going to call z. So this is related to the data. Essentially, it's a transformation of the data to deal with the non-linearity that is inherent in generalized linear models because of the link function. Okay, so instead of actually using the data values themselves, we use this, which deals with the non-linearity which is concerned. So you can see that we've got the yi themselves here, but we have this correction to deal with non-linearity. Okay, again, there are things here that we have to estimate using our current guess. Okay, given that, we then do a least squares estimate. So the only difference in this formula from the least squares methods that we saw in chapter 1 is that we've got z here, which we've calculated above, rather than the data, and we've also got this w term, which is a matrix whose diagonal elements are the weights, which we've just calculated. So this formula here on its own is weighted least squares. It's a least squares where you have some weightings for the different residuals, which are given by the w's. So that's what is going on here. And the point is that we're doing this iterative reweighting of this. So once we do this, we have a new estimate of our parameters. So if we started with B1, we now have B2, which is the estimate of the parameters we get from this. And we just keep going. Now, as usual with numerical iterative techniques, basically what we want is for the process to converge. So we want to get to a situation where after enough steps, our estimates of the parameters have essentially stopped changing. So they settle down, so maybe your first few decimal places settle down, then you do it again, and you find that the next few decimal places have also not changed, so you can start using those as your estimates of the parameters. Okay, so you want your parameter values to converge, and then those will be your estimates of the parameters. Okay, so in the notes there's an example which is, so it's example 26, where we do the calculations and we can do them in R for the Beetle data. I'm not going to go through the details of the calculations, essentially because they're not really very interesting. But you can see how convergence happens if you run it for about how many steps is it? 7 steps. So bottom of page 68, you can see the successive parameter estimates, and you can see that to 3 decimal places, the 6th and the 7th are the same. So it looks like at that point, you have pretty much converged to those estimates. So it actually took 7 iterations to get the answer in that case. Okay, so I then want to move on to the beginning of section 3.5, which I will mention in the first couple of minutes. So, in the various R output that we've seen for generalized linear models, we see quantities called the deviants. So in particular, you'll see the residual deviance and the null deviance in R output. So the deviance can be thought of as a measure of model fit. Okay? And in particular, if you have more than one model, you can use the deviance to compare different models. So this is a little bit like analysis of variance for the standard linear model. Okay, you have residual sums of squares for a standard linear model, and if you have nested models, then you can look at the difference between the residual sums of squares in the 2 models, and you can base tests on that difference. Okay, so that's a lot of what's going on in analysis of variance. So in generalized linear models, it doesn't really make sense to think of sums of squares, and an alternative is to use what's called the deviance. So we're going to need to define what the deviance is, see how we can define it for different models, and look at the difference in deviances between different models, and then we can use that as a test statistic. Okay, I think I should stop there because I haven't really got any time to introduce it properly. We'll start off talking about what's called the maximal model. The maximal model is something which we can compare any model to, and that will be the starting point. What happened to